Calculus often feels like it exists entirely in the realm of pure abstraction, but economists use it as a highly precise measuring tape for the chaotic realities of global markets. Up to this point, we've looked at standard indefinite integration, which is a purely theoretical exercise. When you solve an indefinite integral, you don't get a specific answer. You get a continuous, open-ended family of functions, represented by that lingering plus c at the end of the equation. To make integration actually useful for measuring real-world value, we have to introduce a disruption to the formula, the limits of integration. By capping the function with a lower limit and an upper limit, we force those infinite possibilities into a defined space. The result is no longer an abstract equation, but a hard, singular number. This process, called definite integration, is the critical bridge that allows us to extract a precise, measurable physical value from an otherwise continuous and unbounded mathematical universe. So, what does that hard number actually represent in physical space? This graph shows a standard upward trending curve, specifically the function y equals x squared. To apply definite integration, we set our boundaries, looking at the space on the horizontal x-axis from the lower limit of 1 to the upper limit of 2. The area trapped vertically between our curve and the horizontal axis, bounded by 1 and 2, creates this exact solid orange shape. The problem is that standard geometry fails here. You can easily measure a perfect square or a straight-edged triangle, but formulas for those shapes can only roughly approximate an area that has a sweeping curved roof. Definite integration calculates the exact, perfectly accurate area of that awkward orange space, proving its mathematical utility over basic geometry anytime we deal with curves. For a definite integral, we place a lower limit of 1 at the bottom, an upper limit of 2 at the top, and x squared inside. Step 1, we temporarily ignore limits and integrate x squared, getting x cubed over 3. We drop the plus c constant as it mathematically cancels out. With the integrated function ready, we calculate the specific value between our limits. First, we substitute our upper limit, 2, in for x to get 2 cubed over 3. Next, we substitute our lower limit, 1, giving us 1 cubed over 3. We subtract the lower limit's value from the upper limits. 8/3 minus 1/3 leaves exactly 7/3. This two-step process, integrating the function, then subtracting the lower limit's output from the upper limits, provides the framework to precisely quantify any bounded space. We can now take this mathematical tool and apply it directly to the psychology of human buying behavior in a marketplace. Economists measure the benefit buyers get from a market using a metric called consumer surplus. Consumer surplus is the hidden financial benefit received when buying an item for a price lower than the absolute maximum you are willing to pay. We plot a downward sloping demand line where price equals 36 minus 6Q. The market settles at an equilibrium price of 12, meaning 4 units are purchased. The consumer surplus is located strictly under the demand line but above that fixed equilibrium price. This shaded triangular area translates directly to human behavior. It is the measurable financial value extracted by consumers simply by participating in this market. Because this demand curve was drawn as a perfectly straight line, we can verify our calculus by running a stress test against simple geometry. Using the geometric formula for a triangle, 1/2 base times height, we calculate a surplus area of 48. To verify with calculus, we set up the integral of our demand function from 0 to 4, calculating the entire area down to the 0 axis. That total area includes the money actually spent, so we have to make an adjustment by subtracting the total revenue paid by the consumers. Total revenue forms a literal rectangle on our graph, bounded by 12 and 4. We subtract this revenue rectangle, 12 times 4, or 48, from our integrated demand function. Substituting our limits and subtracting the rectangle leaves a result of exactly 48. The calculus method matches the geometry exactly. This verifies that definite integration is mathematically sound for quantifying value within economic models. We can flip our economic perspective away from the buyers looking for deals and over to the sellers looking for profit. Producer surplus is the benefit sellers reap when charging a market price higher than the absolute minimum price they were willing to accept. We track seller behavior using an upward sloping supply line. Let's use the function price equals 4 plus 2Q, hitting that same equilibrium point. Geometrically, producer surplus lives exactly below the equilibrium price line, but above the supply curve. To set up the calculus equation, the subtraction order flips. We take the solid total revenue rectangle and subtract the integrated area under the supply curve. Our total revenue is 48. We subtract the 32 area under the supply line. That leaves us with a final producer surplus value of 16. The mechanic of definite integration is universally adaptable. It perfectly quantifies the specific financial value extracted from a market, whether calculating for consumers or producers. By locking these two separate perspectives together, we get a single, unified view of the entire market ecosystem. The combination of these two colored areas represents total market efficiency, the maximum possible benefit shared between buyers and sellers. Because our calculus proved accurate, we can extract universal formulas. For consumer surplus, take the definite integral of the demand function and subtract price multiplied by quantity. For producer surplus, take price multiplied by quantity and subtract the definite integral of the supply function. Tracking these integrated areas allows economists to measure the exact health and wealth generation of an entire economic system at a single glance. Which brings us to a final question. If basic geometry easily solved these examples, why use complex calculus at all? The reality is that the straight, linear lines we use today were simplified models designed strictly for educational purposes. True global markets are driven by erratic behaviors that never move in perfectly straight lines. Apply standard geometric formulas to these curves, and the math ceases to be accurate. But definite integration adapts, perfectly hugging the contours to lock down the exact shaded area. This precision demonstrates how mathematics functions as a necessary lens for perceiving the actual scale and value within a market. Definite integration provides the specific framework required to identify and measure value within the unpredictable, nonlinear reality of human economics.